morning all. So today we will discuss about module 3, that is a gate level and data flow modeling. So in previous classes we have to discuss about a data types and some ports declarations, how to declare a ports, and we have to mention some directives in previous classes. So based on the directives, values, its data types, so we have to write a coding part here. So that is a gate level modeling and data flow modeling. So module 3 can be divided into two parts. The first part is a gate level modeling and second part is a data flow modeling. So first we have to discuss a gate level modeling. So there are 4 levels of description in Verilog HDL. The first one is a gate level description, then data flow description, behavioral description and switch level description. So out of this, so gate level description is a low level description. So first go with what? A low level description. So that's why first we discuss a gate level modeling, that is gate level modeling is a part A of, that is module 3, then second part is a data flow modeling. So these are all the what a learning objectives belongs to gate level modeling. We will discuss later, that is data flow modeling learning objectives. So here first identify logic gate primitives provided in Verilog. First we identify which one is the a primitive, which one is the logic gate primitive. So for example AND, OR, then XOR, XNOR, these are all the primitives. First we identify the primitives. The second one, understand instantiation of gates, gate symbols and truth table for AND, OR and buff bar NOT gates. So here understand the instantiation. The instances part we already studied in first module. We discuss first module, that is instances as well as instantiation. Here we discuss in detail about instantiation of gates, then gate symbol, then we have to consider a truth table for AND and OR. So here it's divided into two classes for a primitives here. The first one is AND OR, the second one is buff NOT. That is the what a second learning objective. Then next, understand how to construct a Verilog description from a logic diagram. In other descriptions we have to write the based on truth table and equation, but here understand how to construct Verilog description from logic diagrams. It means first we have to write the logic diagram, then next based on that logic diagram we have to instantiate each gate, then we write the coding. Okay, that is what for learning objective, third learning objective. Next you have to discuss some topics related to gate level modeling, that is describe rise, that is what do you mean by rise time, then fall time, then turn off time, then what do you mean by min type delay, then maximum type delay, then as well as a type delays in gate level description. So these are all the what a learning objectives with respect to gate level modeling. The first topic for the gate level modeling is gate types. So here usually we know that the logic circuit can be designed using a basic logic gates only. That is usually the logic circuits. So it may be a mux, it may be a full adder and half adders. So that can be designed by using a basic gates, right? The basic gates usually we classified into two types here. That is gate types can be classified into two types. The first one is AND OR, then second one is that is buff bar NOT. So NOT or it may be a inverter. Based on this classification we have to represent each and every gate here. Okay. So again I repeat, gate types. So usually the logic circuit can be designed by using a basic gates. Okay. So here gate types can be classified into two types based on Verilog HDL. That is the first one is AND bar OR representation, the second one is buffer bar NOT, that is NOT or it may be inverter representation. First we have to discuss about AND and OR. So here there are 6 primitives are available, 6 gates or representation are available in AND and OR, that is the first one is AND, then second one NAND, then third one OR, then fourth one NOR, then next one is XOR, then XNOR. So these are all the what gates belongs to a Verilog HTL. So that is belongs to only a gate level modeling only. So we can't use these primitives in data flow description, and as well as we can't use in a behavioral description. We should use this primitive in a gate level modeling. Once you represent primitives, next we have to write a logic symbol of each primitive. So we know that logic symbol of AND, that is AND, then next one NAND, then next one is OR, then NOR, then next one XOR, then last one XNOR. Usually in digital logic circuits or digital system design, the gates can be classified into three types. First one we called as a basic gates, then second one we called as universal gates, then third one we called as special gates. Okay, the basic gates are AND or inverter, then special gates are XOR and XNOR, then universal gates are NOR and NAND. But usually when you consider with respect to gate level modeling, with respect to Verilog, classified into AND or then buffer NOT. So these are all the what a symbols it belongs to a gate level modeling. Here we have to represent the inputs and outputs. So usually only one output with respect to what these basic gates. So there are many inputs. It depends on the what a design circuit, but only a one output, that is we called as one scalar output. Then there are multiple scalar inputs are available with respect to primitive gates. Just we name it the what inputs and outputs. So here we can name it as I1, then I2, then out. Here also I1, I2, out. Out. So these are all the what a representation of a inputs and outputs with respect to a and OR. Okay. Next we have to write the what a truth table with respect to these gates. The first truth table we have to consider, it's an AND gate. Okay. So here you name it as AND, then these are all the output or input. So you name it as this is the input 1, then this is the input 2. So usually when you write the truth table, we have to, here let us assume two inputs one. So usually two inputs, there are four combinations. When you design the what a digital electronics, you consider only a four combinations. But we are not considering don't care and high impedance. But here we have to consider a don't care and high impedance, then we write the truth table. Okay. Then first we have to consider a 4 by 0, 1, then X and Z. So here also 0, 1, X and Z. So in AND gate, any one of the input is 0. Then what is the output? Obviously it's 0. Then when any one of the input is 0, then obviously output is 0. Okay. Next here the second combination input is what? I in 1 is 1, then 1 0, it's 0 only, then 1 1, then obviously it's 1. So next one is 1 into X, then what's the value of output is? Then X, then 1 into Z, the value is X. So here the 1, the value of X is either 0 or 1, then X is equal to 0, 1 into 0, that is x value, it's 0 only. Okay, then x is equal to 1, here also 1 into 1, 1, that's the value is x. So that is the representation of when 1. Then next we consider x. So we know that any one of the input is 0, that is sign is equal to 0, here 0 only. Then x into 1, it's x only, then x into x, x, then x into z is x only. Next we have to represent last one, that is z. So we know that any one of the input is 0, then obviously it's 0, then it's an x value. So based on this representation we have to what design the logic circuit. This is the operation of AND 1. Next we have to write for NAND. Again 0 1 x z we have to consider here, 0 1 x and z. So it's exactly what opposite of with respect to AND gate. In terms of what, a ones and zeros only, there is no changes with respect to z and don't care. Then here what is the speciality of NAND gate? Then when it is 0 0, it's exactly opposite of what, a AND gate only. So here 0 0 0 0, here 0 is replaced 1, then here, okay, then here also it's 0. Next we have to write in terms of a don't care. So what's the changes in don't care? There is no changes with respect to don't care. So don't care is what, it's as usual. So based on this one we have to write the what, a NAND operation. So next we know the OR gate operation. So here what is the speciality of OR gate? Then any one of the input is high, and that time output is high. Then all the inputs are 0, then output is 0 only. When you consider here, when it is 0 0, it's 0 only. When it is 0 1, 1, 0 into x. So it depends on the what, x value. So that's why you write x. Again it depends on the z value. Again you write a don't care. Then after this next one, 1 0, 1 0, then 1 only, then 1 1 1, then 1x. Again it depends on don't care. So you write 1x. If x is 0, then on that time 1 0 is 1 only. When x is 1, 1 1 is 1 only. That's why we write 1 here. So here it separates z also, it's 1. Next we consider don't care here. Then 1 0, 1 only, then 0 0. So that's why we write x here. Next any one of the input is I. You simply write 1. Then xx is x, then x. Then last one we have to operate with respect to I impedance. It's z, x is 0 is x only. Then any one of the input is I. Then I. Then here x. Then x. This is the what, a representation of OR gate. Next we move on to NOR gate. NOR gate is what, exactly opposite of OR gate. So here 0 0 it's 1. Then 1 0. 1 0 is 0, then x, x, then 1 0, 0, then 1 1, 0, then 1 into x, 0, 0. Then next here you have to operate don't care, that is x, then it's 0, x, x, then z you have to consider I impedance here, x, 0, x, x. This is the what, a truth table belongs to NOR gate. So in usually when you write the a Verilog code, we should consider a don't care and I impedance. So that's why in all the truth table we have to consider don't care and I impedance. So XOR and XNOR we call it as special gates with respect to a digital system design. Then when it is 0 0, obviously it's 0. When it is 0 1, when it is 0 1, it's 1. Then 0x, it depends on the what, a don't care value x, so that is x. Then again z, it depends on a impedance, that is x. 1 0, then 1 0 is 1, 1 1, it's 0, that is 1x. it depends on the what? A don't care value. We have to write a don't care here. Next we have to consider don't care with 0. Then don't care with 0, it depends on don't care. We can write x. Again don't care with 1, it depends on don't care. X and x, that is don't care with don't care, it depends on don't care. Don't care with high impedance, it depends on don't care only. Next last one we have to consider here, don't care. Okay, it depends on 0, 1, xz. Obviously all are what? A don't care words. So this is the what? A truth table for XOR gate. Next move on to XNOR gate. So here when it is 0 0, it's exactly opposite, that is 1 0 1 0, then there is no changes with respect to don't care. 1 0 0 1 1 1, no change. Then remaining all are what? A don't care. So this is the what? A truth table for XNOR. So based on the truth table, then as well as the gates, next we have to instantiate a gate level description. So based on these gates, we have to write the instantiation here. We are not mentioned inputs and outputs. It's not a what complete program. So usually inputs and outputs, it's represent in terms of a wire, that is a net. So first here out can be represent out, then IN1 can be represent IN1, then IN2 can be written as capital IN2. So based on this we have to write here code. So first wire, how many wires here? How many nets? So there are 3 nets here, that is wire out, then IN1 and then IN2. Okay, then after this we have to instantiate each and every gate. We know the condition of instantiate. The first terminal is always output, the remaining terminals are the what? Inputs. The first terminal output here. Next we have to consider the first gate, that is AND gate. So here AND, so name of the instantiation you have to write A1 or you can write any name, and A1, then here. So we have to mention the first is what? The first is represent output terminal, that is out, then IN1, IN2. So next we have to consider another gate, that is a primitive word is what? NAND, you name it as A2. So here out, then IN1 and IN2. Okay, similarly for XOR A3, then out IN1, then IN2. So next for XNOR gate, you name it as A4, then out IN1, then IN2. Next we have to write a OR is primitive, then OR, then A5, then out IN1 and then IN2. NOR gate we have to write, NOR is a predefined word. Here you have to write the first terminal is out, then name of the NOR is A6, then out, then IN1 and then IN2. Okay, these are all the what it belongs to a 2 inputs basic gates. So here only 2 inputs as well as a single output. Suppose there are multiple number of inputs, there are 3 inputs we have to assume, and that time for 3 inputs let us assume for AND gate. So AND, so you simply name it as gate name A7. Okay, suppose there are 3 inputs, and that time there is no changes with respect to the first terminal. The first terminal is always same, that is you have to declare out only. Okay, there is no change. So suppose 3 inputs, and that time you have to mention here IN1, then IN2, then IN3. This is all the what it belongs to when you consider a 3 input one. Suppose one more representation is there, so that can be written as, this can be replaced, and out IN1, then IN2, then IN3. So what's the difference here? The difference is, here we have to name the name of the instantiation. Name of the instantiation is what? A7. But here we are not take instantiation name. So this is also correct. Okay. Suppose there are some multiple gates operation, and that time you should use instantiation. Okay. But a single gate we are using, and that time there is no name required for instantiation.